Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at some very nice applications of the intermediate value theorem. Let me recall what is the intermediate value theorem. One way to state is that suppose I is an interval and f is a continuous function, important, then the image of f itself is an interval. So continuous image of an interval is an interval. That's what the function is saying, that's what the theorem is saying. And one particular instance or corollary of this is that if a continuous function defined on an interval takes a positive value and a negative value, then it also takes the value 0 somewhere. That's just a very straightforward corollary of this statement. And we in fact saw a proof of it independently in the previous lecture. In fact, this is how we proved this statement. First we proved this corollary and then we proved this. Anyway, so this is the statement of the intermediate value theorem. Now let us look at some applications. So our first application will be the following. So suppose we have a continuous function from the unit interval to the unit interval. Then we want to show that there is a point in the unit interval which f does not disturb, meaning it is left fixed by the function f. Such a point is called a fixed point for obvious reasons. So basically this is saying that every continuous function of this sort has a fixed point. Let me make a remark that this won't be true any longer if we replace this by the open interval. So let us just note that the map from the open interval to itself, which takes little x to x square, has no fixed points. So this is a simple exercise, because if there were a fixed point, then x would equal to x square, and the only solutions of this would be 0 and 1, but 0 and 1 are not present in the domain. So that's just a simple counterexample in case one wants to improve this theorem to arbitrary intervals. So one can't. Also, one can easily show that continuity is also an important hypothesis. If you simply drop this hypothesis, then you can easily find counterexamples, so I won't be doing that. Anyway, so let's look at a proof of it. And before we even look at a proof of it, let us just look at the picture as to what is the idea. So here we have the function. We'll draw the graph of the function later. Suppose first we draw this line, which is the graph of the identity function. The identity function, recall, is the function which takes little x to x. So this is 1 and this is 1. Okay. And now if f0 equals 0, then we are done, because then 0 is a fixed point. So let's say f0 is positive. It has to be. If it is non-zero, then it has to be positive, because it is only, we are already given that f takes value in this interval. Alright. And now if f of 1 equals 1, then again we are done, because then 1 would be a fixed point. So suppose f of 1 is strictly lesser than 1. It's, let's say, somewhere here. And now since the function is continuous, the graph of the function will intersect this line somewhere. And wherever it intersects this line, you just take the point corresponding to the intersection. So let's call that point x0. And clearly f of x0 equals x0. Simply because this is x0. The reason being, this is the graph of the identity function. So this is a 45-degree line. So if this is x0, then that is x0. So this is the main idea of the proof, and we'll have to express this properly. One can't just draw a picture and say that it's done. One has to write a formal proof. So here is a formal proof. Okay, so define the map g from the unit interval to real numbers as g of x equals f of x minus x. Right? So we are only recording this value. In this particular figure, we are recording this value. So at a point x, this is what g returns, this length with sign. So here g will return negative, or rather, yeah, here g will return negative because f of x is smaller than x. Here g will return positive. Okay, so that, forget about the picture. The proof will not make reference to the picture, but one needs to reinforce understanding by the picture. Anyway, now if g0 is 0, then f0 is 0, and hence 0 is a fixed point. Basically, hence we are done. And if g1 equals 0, then again f of 1 minus 1 would be 0, which would imply f of 1 equals 1, and then again we would be done. So we may assume that g of 0 is non-zero and g of 1 is non-zero, because in these two cases, if any of these two cases don't hold, then we are already done. Okay, now what could g of 0 be? Therefore, g of 0 has to be positive, because f of 0 then has to be positive. F takes value only in the unit interval, and if f of 0 is non-zero, then f of 0 is positive, and hence g of 0 is positive. Also, g of 1 would have to be less than 1 by the same reasoning, because f is valued in the unit interval. If f of 1 is not equal to 1, then f of 1 is strictly less than 1, and hence g of 1 is strictly, what have I written? This is strictly less than 0. So once again, since f of 1 is assumed to be strictly less than 1, this thing at x equals 1 has to be strictly less than 0. So we have these two things. And now lastly, this is the most important point, that note that g is continuous. Why is g continuous? Because g is the difference of two continuous functions. We discussed the algebra of continuity, and there was a lecture named with that title. So what is g? G is the difference of f and the identity map, and therefore g is continuous. So just please take a note. And therefore, by the intermediate value theorem, thus by the intermediate value theorem, we know that there is some point x0 in the domain of g. In fact, here one can say that it is strictly between 0 and 1, such that g of x0 is 0, which means f of x0 equals x0, and we are done. So that's it. So I took very long to prove this, but I hope it cannot hurt to spend time on a theorem. It may get a little bit boring though. Anyway, so very simple. The proof is not at all hard. It's just one idea. The hard work has already been done when we proved the intermediate value theorem. Alright, so now let us look at another very nice fact, that odd degree polynomials always have a root, always have a real root. So let me precisely say what I want to say. First, let us recall the definition of a polynomial. So a function p from reals to reals is called a polynomial of degree n, where n is some positive integer, if there exist a0, a1, ... an real numbers with an non-zero, such that p of x equals an x to the power n plus a n minus 1 to the times x to the power n minus 1 plus ... plus a1x plus a0. So that's a polynomial of degree n, and we say that it is an odd degree polynomial if n is odd. So this is called the leading term for obvious reasons, and just note that this is not allowed to be 0. So an odd degree polynomial, for example, would be something like x cube, by which I mean px equals x cube. If this is the definition of p, then p is an odd degree polynomial because you have 3 here. 3 is an odd number. This as well, and now if you add anything of lower degree, then it still remains an odd degree polynomial. So yeah, so that's fine. Now if we look at the graph of, let's say, just x cubed, then what we find is it looks something like this. So this is the x-axis, this is the y-axis, and we see that it has a 0, it has a root, meaning it vanishes at some point. So let me also make that definition. So let p be a polynomial then we say that a real number x0 is a root of p if px0 is 0. So we made two definitions. Polynomials we had already defined, but anyway, root perhaps we did not define. Okay. So I'm sure all of this is familiar from high school, and let me just also note that not all polynomials have a root. For instance, if p is defined as p of x equals x squared plus 1, then p has no roots. Simply because this is always positive. This is strictly positive always. Therefore, it cannot have a root. So it's not true that all polynomials have a root. However, it is true that all odd degree polynomials have a root. And that is what we want to show. So here is the theorem. Let p be an odd degree polynomial then p has a root. So let us first see the idea, and to see the idea, let us fix some concrete polynomial. So let's say px is behaving like something like this. Let's say 2x plus 1. This is my particular px. So if we plot the graph of the function, if x is too big, something like 1,000,000, then this is definitely positive. In fact, this is positive for all x. So let me put a minus here just so that I have a better example. So now if x is too big, then this kind of fades in comparison to this guy, because this is a cube and this is just a linear kind of term. So if x is very big, like 1,000,000, then clearly this has to be positive. So it takes positive value somewhere here. And now if you feed something far on the left side of the real line, meaning something negative but of huge magnitude, meaning something like some point here, this distance is very large, then again this thing would surely be negative, because this again pales in comparison to the effect of that guy. So it takes negative value somewhere, and therefore by intermediate value theorem and the continuity of polynomials, the polynomial also should vanish somewhere. And that's basically what we want to execute. So again, drawing a picture and all this heuristics is not a proof. This is what leads to a proof. However, one needs to still write the proof. And now we are going to do it. So here is the proof. Let px equals an x to the n plus an minus 1 x to the n minus 1 dot plus a1x plus a0, where n is odd and an is non-zero. And in fact, let me assume that an is positive. Hardly matters, but just for convenience I'll assume that an is positive. The same proof will go for negative an. Okay, so what we'll do is the following. Note that, or rather we have p of x is, we forcefully bring out the leading term, so p of x is equal to that thing for x non-zero. If x is 0, then we can't do this. Alright, fine. Now the point is the following. So if x has huge magnitude, then this number is very, very small in magnitude, and hence this would surely be positive, right? So if you just take a very huge magnitude of x, this remains positive. But if x is of huge magnitude but at the same time a positive number, then this whole thing would remain positive. And if x is of huge magnitude and a very negative number, then this whole thing will become negative, and therefore px by the intermediate value theorem will have to take the value 0 somewhere. So that's the idea. And how do we execute it? So let m greater than 0 be such that let's say ai, or let me write an minus I one upon m to the power I in the absolute value is smaller than 1 by 2n. And you'll see why have I chosen this 1 by 2, and I could have chosen 1 by 10n or anything. A lot of things could work here, but I have just chosen this for convenience. So once we have chosen that, then P of m equals an m to the power n 1 plus this monstrosity, which implies that P of m is greater than right. So maybe before even I get there, I should explain why such an m exists. Why is there an m here at all which satisfies this? Again, I should also say for all I equals 1 to n. So why is there such an m? This is basically this property that infimum of 1 upon k greater than 0. This is 0. There's one way to see this is using this fact. Basically, these are just constants. So if you choose m large and large, if you choose very large m, then of course this becomes as small as you want. And 1 upon 2n is just a constant. N is just a number. N is an odd number, but it's just a number. So this can be made arbitrarily small as you want. And therefore, one can easily show that such an m exists which satisfies this inequality for each such I. Alright. So now I come to why is this implication holding. So we have this equality, and now this thing definitely is greater than that thing. This is by, you could do some basic algebra, or you could use the triangle inequality. Or in fact, you don't even need the triangle inequality. You just convince yourself that this is greater than that. Nothing big going on there. And since this is a positive number, we have already assumed that an is positive. So this does not change the sign. Alright, so we have this inequality, and now this thing is greater than 1 minus 1 upon 2n dot 1 upon 2n. Because this thing is less than 1 upon 2n. So minus of that thing is greater than minus 1 upon 2n, and that's what we have done here. So I just use this for each of these terms and got that. And this gives me 1 minus half. Because if I sum 1 upon 2n n times, then I get a half. And that's the reason why I chose a half, because then I get something positive here. So this is some positive number. Basically, this is half of a and m to the n. This is some positive number. Similarly, p of minus m is a negative number. The exact same reasoning. And we are done. And therefore, right, so why is p of minus m a negative number? Here is where we use the fact that n is odd. Because once you put minus m to the power n, and since n is odd, sorry, I should write minus m to the power n, and since m is odd, this is a negative number. And this is the reason why this proof does not go through for even power, even degree polynomials. And it shouldn't go through for even degree polynomials, because as we've seen, it is false for even degree polynomials. X squared plus 1 is an even degree polynomial which does not have a root. So similarly, this thing also holds, and therefore by the intermediate value theorem, since polynomials are continuous, we have that p has a root. And that's it. Again, I took too long to give a proof of this, but I don't want to miss any detail. Okay. So very nice, and not a trivial fact that a polynomial function has a root provided some simple conditions are satisfied. All right. So now let us look at some more easy consequences. So the first one is something that I won't write the proof of, but let me state it. So suppose n is greater than or equal to 1. You can take 2 as a concrete example. Then we want to show that this function, which is defined like this, it just takes x and produces the nth power of x. That is a bijective function. So how do we do it? So for what do we want to do? What do we want to show when we are faced with showing bijectivity? We want to show injective and surjective. So is it injective? This is injective simply because this is a monotone function. If injectivity of f follows from monotonicity, if x less than y, then and positive. So because the domain of f is just non-negative real numbers, then x to the n is less than y to the n. So this gives you injectivity. And for surjectivity, we'll use the intermediate value theorem. This is the intermediate value theorem, and I won't be writing this proof, but let me explain what is happening and leave the details as an exercise. So clearly f takes the value 0 at 0. This is the value of the function at 0, and f takes arbitrarily large values. If x is larger and larger, then this value is also larger and larger. So there is no upper bound on the values that f can take. And of course it takes only positive values. So that means since the image of f has to be an interval by the continuity of f, this function is continuous as we've seen before. So the image of f is an interval, and it takes the value 0, or it takes all, what should I say? It takes larger and larger values, meaning there is no upper bound on the values that f can take. It should take all the values that are there on the non-negative real line. So that's it. Therefore it is surjective and hence bijective. Alright. And maybe I want to do a little bit. Okay, yeah. So let me do this corollary, which is that let n be greater than or equal to 1. Then for all x greater than 0, there is a unique y greater than or equal to 0, such that y to the n equals x. Meaning there is a unique non-negative nth root of x. So in other words, this is the case. And remember that we proved that square root of non-negative real numbers exist, and we did some longish argument to do that. Here we have just a one-line argument. Basically this theorem is immediately telling you that such a y exists, and it is unique because this function is bijective. So very nice proof. We did not have to do any estimates. It's just a consequence of the intermediate value theorem, that not just square roots exist, but cube roots, fourth roots, fifth, whichever root you want, it always exists as long as you have a non-negative integer. Alright. And lastly, okay, so I'll leave this thing as an exercise, the last part, that let n be odd. So if we have an odd integer, then the function, and note the domain and the target, which takes x to the power n, is bijective. So this is an exercise. Clearly this is false if n is even. Even for the square function we see graphs like this. That's not an injective function. Alright, so yeah, this is all that I wanted to do today. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.